So far we've defined random walks using for loops, using while loops, and we've written a function that takes two inputs. Let me remind it to you. EV, expected value, walk 1. It takes two inputs. The first one is how many steps do we take. So for example, let's take 20 steps. And the second one is how many experiments do we run. So the bigger this is, the more accurate our expected value should be. So let's do 200. So what this is saying is that on average, when we took 200 experiments and did 20 steps, we ended up 3.58 units away from the origin in this for loop random walk. So I looked up on the website Math Stack Exchange what the formula is for this, because it's not at all easy to see what's the formula that, for example, takes input 20 and output something similar to 3.58. And it turns out it's a really random looking formula. It's not exactly correct for any given input n, so it's not exactly correct for this 20, but it becomes more correct the bigger n is. So this is some sort of limit formula. And what's the formula? Well, it's a hint that these random walks are very interesting. The formula actually involves pi, which is really interesting considering that we're just adding ones and negative ones. Okay, there's nothing at all irrational or transcendental about this process, but still the formula, it's going to involve square roots, so something irrational, and it's going to involve pi, something transcendental. So let me show you what the formula is in this specific case. It's square root of 2 times n, which in this case is 20, divided by pi. So I love these kind of random looking formulas. There's also some similar random looking formula for Fibonacci numbers that maybe we'll talk about later. So there we go. It's even very close to this 3.58. So to convince you that it's even closer than maybe this indicates, let's create a script that plots both the function square root of 2x over pi and some of these expected value of walk 1 numbers. So let me do that in a script. And I've played around to try to find numbers that don't take too long to run. So the numbers I ended up choosing were start at 10, go up by 10, stop at 500. So the reason I called this x was because when I do the plotting, these are going to be the x values, and these stand for how many steps we take. So here I took 20 steps. For these, we're going to take 10 steps, then 20 steps, all the way up to 500 steps. And we're going to plot two different things, so I need two different y vectors. I'll call them y1 and y2. y1 is going to be the easier one. It's just square root of 2 times x over pi. y2, it's going to involve our expected value formula. So for I equals x, so that means that I first is going to be 10, then is going to be 20, all the way up to 500. And for each of these values of I, on y1, I'm going to put square root of 2 times I over pi at the end of it. For y2, I'm going to put expected value of walk 1 for I steps and 5,000 tests. And then I'm going to plot these. I'm going to plot xy1 just using the default parameters, which will be a blue solid curve. And then I'm going to plot xy2. And these I'm going to plot a little differently. I'm going to use black for my color. I'm going to mark them with X's, and I'm not going to connect them with any kind of line. So I'll save it. Let me call it as test walk. And now let me run it. And it's going to take a little bit of time, so I'm going to pause the video and come back. So now the formula has finished running, or the script has finished running, and we can look at it. Here's the plot that it generated. So you can see that especially for these smaller values of n, so the ones where we take a smaller number of steps, especially for those, this formula fits very closely to the formula square root of 2 times n over pi. And I think that's really cool that this formula involving pi shows up in something very natural, just some average related to this simple type of random walk.